In petroleum geology and chemistry, cracking is the process whereby complex organic molecules such as kerogens or long-chain hydrocarbons are broken down into simpler molecules such as light hydrocarbons, by the breaking of carbon-carbon bonds in the precursors. The rate of cracking and the end products are strongly dependent on the temperature and presence of catalysts. Cracking is the breakdown of a large alkane into smaller, more useful alkanes and alkenes. Simply put, hydrocarbon cracking is the process of breaking a long chain of hydrocarbons into short ones. This process might require high temperatures and high pressure. More loosely, outside the field of petroleum chemistry, the term cracking is used to describe any type of splitting of molecules under the influence of heat, catalysts and solvents, such as in processes of destructive distillation or pyrolysis. Fluid catalytic cracking produces a high yield of petrol and LPG, while hydrocracking is a major source of jet fuel, diesel fuel, naphtha, and again yields LPG. History and patents. Among several variants of thermal cracking methods, Vladimir Shukov, a Russian engineer, invented and patented the first in 1891. One installation was used to a limited extent in Russia, but development was not followed up. In the first decade of the 20th century, the American engineers William Merriam Burton and Robert E. Humphreys independently developed and patented a similar process as U.S. Patent 1,049,667 on June 8, 1908. Among its advantages was the fact that both the condenser and the boiler were continuously kept under pressure. In its earlier versions, however, it was a batch process, rather than continuous, and many patents were to follow in the USA and Europe, though not all were practical. In 1924, a delegation from the American Sinclair Oil Corporation visited Shukov. Sinclair Oil apparently wished to suggest that the patent of Burton and Humphreys, in use by Standard Oil, was derived from Shukov's patent for oil cracking, as described in the Russian patent. If that could be established, it could strengthen the hand of rival American companies wishing to invalidate the Burton-Humphreys patent. In the event, Shukov satisfied the Americans that in principle Burton's method closely resembled his 1891 patents, though his own interest in the matter was primarily to establish that the Russian oil industry could easily build a cracking apparatus according to any of the described systems without being accused by the Americans of borrowing for free. At the time, just a few years after the Russian Revolution, Russia was desperate to develop industry and earn foreign exchange, so their oil industry eventually did obtain much of the technology from foreign companies, largely American. At about that time, however, fluid catalytic cracking was being explored and developed and soon replaced most of the purely thermal cracking processes in the fossil fuel processing industry. The replacement was, however, not complete. Many types of cracking, including pure thermal cracking, still are in use, depending on the nature of the feedstock and the products required to satisfy market demands. Thermal cracking remains important, however, for example in producing naphtha, gas oil, and coke. More sophisticated forms of thermal cracking have been developed for various purposes. These include visbreaking, steam cracking, and coking. Chemistry. A large number of chemical reactions take place during the cracking process, most of them based on free radicals. Computer simulations aimed at modeling what takes place during steam cracking have included hundreds or even thousands of reactions in the models. The main reactions that take place include initiation. In these reactions, a single molecule molecule breaks apart into two free radicals. Only a small fraction of the feed molecules actually undergo initiation, but these reactions are necessary to produce the free radicals that drive the rest of the reactions. In steam cracking, initiation usually involves breaking a chemical bond between two carbon atoms, rather than the bond between a carbon and a hydrogen atom. CH3CH32CH3 hydrogen abstraction. In these reactions, a free radical removes a hydrogen atom from another molecule, turning the second molecule into a free radical. CH3 plus CH3 CH3 CH4 plus CH3 CH2 radical decomposition. In these reactions, a free radical breaks apart into two molecules, one an alkene, the other a free radical. This is the process that results in alkene products. CH3CH2CH2 equals CH2 plus H radical addition. In these reactions, the reverse of radical decomposition reactions, a radical reacts with an alkene to form a single, larger free radical. These processes are involved in forming the aromatic products that result when heavier feedstocks are used. CH3CH2 plus CH2 equals CH2 CH3 CH2 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 termination. In these reactions, two free radicals react with each other to produce products that are not free radicals. Two common forms of termination are recombination, where the two radicals combine to form one larger molecule, and disproportionation, where one radical transfers a hydrogen atom to the other, giving an alkene and an alkane. CH3CH2 plus CH3CH2 CH2 equals CH2 plus CH3CH3 Example, cracking butane. There are three places where a butane molecule might be split. Each has a distinct likelihood. 48% break at the CH3CH2 bond. CH3 asterisk CH2 CH2 CH3. Ultimately this produces an alkane and an alkene. CH4 plus CH2 equals CH3. 38% break at a CH2 CH2 bond. CH3 CH2 asterisk CH2 CH3. Ultimately this produces an alkane and an alkene of different types. CH3 CH3 plus CH2 equals CH2. 14% break at a terminal CH bond. CH2 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 CH3. Ultimately this produces an alkene and hydrogen gas. CH2 equals CH2 CH3 plus H2. Cracking methodologies. Thermal methods. Thermal cracking was the first category of hydrocarbon cracking to be developed. Thermal cracking is an example of a reaction whose energetics are dominated by entropy rather than by enthalpy. In the Gibbs free energy equation, increment G degree equals increment H degree T increment S degree. Although the bond association energy D for a carbon-carbon single bond is relatively high and cracking is highly endothermic, the large positive entropy change resulting from the fragmentation of one large molecule into several smaller pieces, together with the extremely high temperature, makes D increment S degree term larger than the increment H degree term, thereby favoring the cracking reaction. Thermal cracking. Modern high-pressure thermal cracking operates at absolute pressures of about 7,000 kilopascals. An overall process of disproportionation can be observed, where hydrogen-rich products are formed at the expense of heavier molecules which condense and are depleted of hydrogen. The actual reaction is known as homolytic fission and produces alkenes, which are the basis for the economically important production of polymers. Thermal cracking is currently used to upgrade very heavy fractions or to produce light fractions or distillates, burner fuel and/or petroleum coke. two extremes of the thermal cracking in terms of product range are represented by the high-temperature process called steam cracking, or pyrolysis, which produces valuable ethylene and other feedstocks for the petrochemical industry, and the milder temperature delayed coking, which can produce, under the right conditions, valuable needle coke, a highly crystalline petroleum coke used in the production of electrodes for the steel and aluminium industries. William Merriam Burton developed one of the earliest thermal cracking processes in 1912, which operated at 700 to 750 degrees Fahrenheit and an absolute pressure of 90. Cyan was known as the Burton process. Shortly thereafter, in 1921, C.P. Dubs, an employee of the Universal Oil Products Company, developed a somewhat more advanced thermal cracking process which operated at 750 to 860 degrees Fahrenheit and was known as the Dubs process. The Dubs process was used extensively by many refineries until the early 1940s, when catalytic cracking came into use. Steam cracking. Steam cracking is a petrochemical process in which saturated hydrocarbons are broken down into smaller, often unsaturated, hydrocarbons. It is the principal industrial method for producing the lighter alkenes, including ethene and propene. Steam cracker units are facilities in which a feedstock such as naphtha, liquefied petroleum gas, ethane, propane or butane is thermally cracked through the use of steam in a bank of pyrolysis furnaces to produce lighter hydrocarbons. The products obtained depend on the composition of the feed, the hydrocarbon to steam ratio, and on the cracking temperature and furnace residence time. In steam cracking, a gaseous or liquid hydrocarbon feed like naphtha, LPG or ethane is diluted with steam and briefly heated in a furnace without the presence of oxygen. Typically, the reaction temperature is very high, at around 850 degrees Celsius, but the reaction is only allowed to take place very briefly. In modern cracking furnaces, the residence time is reduced to milliseconds to improve yield, resulting in gas velocities up to the speed of sound. After the cracking temperature has been reached, the gas is quickly quenched to stop the reaction in a transfer line heat exchanger or inside a quenching head or using quench oil. The products produced in the reaction depend on the composition of the feed, the hydrocarbon to steam ratio, and on the cracking temperature and furnace residence time. Light hydrocarbon feeds such as ethane, LPGs or light naphtha give product streams rich in the lighter alkenes, including ethylene, propylene, and butadiene. Heavier hydrocarbon feeds give some of these, but also give products rich in aromatic hydrocarbons and hydrocarbons suitable for inclusion in gasoline or fuel oil. A higher cracking temperature favors the production of ethene and benzene, whereas lower severity produces higher amounts of propene, C4 hydrocarbons and liquid products. The process also results in the slow deposition of coke, a form of carbon, on the reactor walls. This degrades the efficiency of the reactor, so reaction conditions are designed to minimize this. Nonetheless, a steam cracking furnace can usually only run for a few months at a time between decokings. Decokes require the furnace to be isolated from the process, and then a flow of steam or a steam-air mixture is passed through the furnace coils. This converts the hard solid carbon layer to carbon monoxide and carbon dioxide. Once this reaction is complete, the furnace can be returned to service. Catalytic methods. The catalytic cracking process involves the presence of acid catalysts which promote a heterolytic breakage of bonds yielding pairs of ions of opposite charges, usually a carbocation and the very unstable hydride anion. Carbon-localized free radicals and cations are both highly unstable and undergo processes of chain rearrangement, C-scission in position beta as in cracking, and intra- and intermolecular hydrogen transfer. In both types of processes, the corresponding reactive intermediates are permanently regenerated, and thus they proceed by a self-propagating chain mechanism. The chain of reactions is eventually terminated by radical or ion recombination. Fluid catalytic cracking. Fluid catalytic cracking is a commonly used process, and a modern oil refinery will typically include a cat cracker, particularly at refineries in the U.S. due to the high demand for gasoline. The process was first used around 1942 and employs a powdered catalyst. During World War II, the Allied forces had plentiful supplies of the materials in contrast to the Axis forces, which suffered severe shortages of gasoline and artificial rubber. Initial process implementations were based on low-activity alumina catalyst and a reactor where the catalyst particles were suspended in a rising flow of feed hydrocarbons in a fluidized bed. Alumina-catalyzed cracking systems are still in use in high school and university laboratories in experiments concerning alkanes and alkenes. The catalyst is usually obtained by crushing pumice stones, which contain mainly aluminium oxide and silica, into small, porous pieces. In the laboratory, aluminium oxide must be heated. In newer designs, cracking takes place using a very active zeolite-based catalyst in a short contact time vertical or upward sloped pipe called the riser. Preheated feed is sprayed into the base of the riser via feed nozzles where it contacts extremely hot fluidized catalyst at 1230 to 1400 degrees Fahrenheit. The hot catalyst vaporizes the feed and catalyzes the cracking reactions that break down the high molecular weight oil into light components, including LPG, gasoline, and diesel. The catalyst-hydrocarbon mixture flows upward through the riser for a few seconds, and then the mixture is separated via cyclones. The catalyst-free hydrocarbons are routed to a main fractionator for separation into fuel gas, LPG, gasoline, naphtha, light cycle oils used in diesel and jet fuel, and heavy fuel oil. During the trip up the riser, the cracking catalyst is spent by reactions which deposit coke on the catalyst and greatly reduce activity and selectivity. The spent catalyst is disengaged from the cracked hydrocarbon vapors and sent to a stripper where it contacts steam to remove hydrocarbons remaining in the catalyst pores. The spent catalyst then flows into a fluidized bed regenerator where air is used to burn off the coke to restore catalyst activity and also provide the necessary heat for the next reaction cycle, cracking being an endothermic reaction. The regenerated catalyst then flows to the base of the riser, repeating the cycle. The gasoline produced in the FCC unit has an elevated octane rating but is less chemically stable compared to other gasoline components due to its olefinic profile. Olefins in gasoline are responsible for the formation of polymeric deposits in storage tanks, fuel ducts and injectors. The FCC LPG is an important source of C3C4 olefins and isobutane that are essential feeds for the alkylation process and the production of polymers, such as polypropylene. Hydrocracking. Hydrocracking is a catalytic cracking process assisted by the presence of added hydrogen gas. Unlike a hydrotreater, where hydrogen is used to cleave CS and CN bonds, hydrocracking uses hydrogen to break CC bonds. The products of this process are saturated hydrocarbons. Depending on the reaction conditions, these products range from ethane, LPG to heavier hydrocarbons consisting mostly of isoparaffins. Hydrocracking is normally facilitated by a bifunctional catalyst that is capable of rearranging and breaking hydrocarbon chains as well as adding hydrogen to aromatics and olefins to produce naphthenes and alkanes. The major products from hydrocracking are jet fuel and diesel, but low-sulfur naphtha fractions and LPG are also produced. All these products have a very low content of sulfur and other contaminants. It is very common in Europe and Asia because those regions have high demand for diesel and kerosene. In the US, fluid catalytic cracking is more common because the demand for gasoline is higher. The hydrocracking process depends on the nature of the feedstock and the relative rates of the two competing reactions, hydrogenation and cracking. Heavy aromatic feedstock is converted into lighter products under a wide range of very high pressures and fairly high temperatures, in the presence of hydrogen and special catalysts. The primary function of hydrogen is, thus, a. preventing the formation of polycyclic aromatic compounds if feedstock has a high paraffinic content, b. reduce tar formation, c. reducing impurities, d. preventing buildup of coke on the catalyst, e. converting sulfur and nitrogen compounds present in the feedstock to hydrogen sulfide and ammonia, and e. achieving high cetane number fuel.